Dear student, today we will be talking about the supervised learning, and in the supervised learning, we will be discussing about the linear regression. So, as we know that in supervised learning, the data is labeled. Okay, we know that what could be the possible output, while in the unsupervised learning, we don't know that how many output would be there, and like let's suppose the number of clusterings could be varying. Sometime it could be giving you two cluster, sometime three or four, depending on the density, depending on the distances. And in the reinforcement learning, we get a feedback, we get a reward, we get a punishment, like kind of thing, and then we fix according to that one. So reinforcement learning, is a kind of a series of reinforcements of rewards and punishment. So by this way, we improve our model. So in supervised learning, as I told you that there are like different kinds of learning, like linear regression, sinusoidal wave, piecewise linear, and degree 12 polynomial. So these are the different examples for two different data sets. In linear regression, that how we define it, that usually it is like a normal equations, in the form of y equal to b like equations, and in that one we know that how the line is changing. So sometime a line could be a tilted one, sometime it will be horizontal, sometime it will be vertical. So depending on the equation and the parameter along with the variables, so which are called dependent and independent variable. So here you can see, so it is not only y equal to b, but we have a y equal to ax plus b. So x is independent variable, and y is dependent on the x. Yeah, so we have to fit a line. For example, in this one, we see that there are when we draw a line, so some of the points on the line would be touching it, but some are not, right? So sometimes we calculate r square is the first step and determine how good the guess will be, right? Just like in the least square, we measure the distance from the mean to the data points and square it, and then add and those square together. So what is r square? It's basically, in simple words, I can say that the distance of the data points from the mean of all the points, okay, and then we square it, right? So that's called r square, right? So we call this as ss, for the sum of the squares around the mean. Here is some very important formulas for us to know. So what is ss mean? Is data minus mean whole square, and then variation around the mean is data minus mean whole square divided by n, okay, and then we have variable mean, which ss of the mean and divided by the n. So here see how we fit the line on the different points. So we see that the same formula we applied, and we see that there is a fitting line, but all the points are not touching that one. And here we also see some formula of the variance. Like for example, variance is the sum of the square divided by the number of all those things. So we call it the average sum of the square. Okay, so sometimes we see less variation around the line, and sometimes we see more variations. So like if you this one, if you see, we can say that some of the variation in the cat size, like last time we had some example of fat cat and not fat cat. So in that size is explained by taking the cat weight into account. So we see the accounts, we see the weights of the cat, and accordingly we decide that whether the cat is fat or not. Like for example, if it is heavier, and the cat is, we see it's bigger, right? And so these lighter cats are usually smaller. So there is more discussion on the R square. R square is very much important in linear regression. So R square tell us how much of the variation in the cat size can be explained by taking the cat's weight into account, right? So it is about playing with the weights of the cat, and then see how it like varies. So according to the formula is very straight forward, like variance of the mean minus variance of the fitting, okay, divided by variance of the mean. So according to this one, the cat weight explains like 60% of the variation in the cat size. If you see with this example, so here, like if you have this data, the two different graphs you have it. So according to this one, like variations is like of variation in the mean is 11, which is very high, right? And on this line, the vertical line is high, while in the tilted line on the left hand side, this one, it's 4.4. So according to this one, yeah. So what should be the R square? So this is the question for you. So in the next slide, we will see that how can we find the R square. So we can also use the sum of the square to make the same calculations as per the definitions. And here are some more results. So R square will be calculated in a few ways. So yeah, so according to this one, the horizontal line, the horizontal line, so only one point is fitting, other 4 points are not, like more away from it. While in this one on the tilted line, the all points, all the 5 points are being like fitted over here. So let's see how the R square is like mean how is the variance. For example, variance of the mean, okay, and variance of the fitting when it is fitting over there. So you will see the changes when I'm moving to the next, like slides, right? So here I say R square is 0. In this case, cat weight doesn't explain any of the variation around the mean. So here, like weight of the cat is meaningless, okay? And cat weight doesn't help us to predict cat size as well. Here, like when calculating SS mean, we collapse the points onto the y-axis jump to emphasize the fact that we are ignoring mouse weight. And on the left, on the right hand side, like mean cat size and calculate SS around that one. Okay, so here is different. Now this is a very interesting picture you can see over here. So on the x-axis we have the weights, and on the y-axis we have the size of the cat. So if the size increases, so the cat will be vertically above. If the weight increases, so it will be horizontally on the right hand side. So imagine we want to know if a cat weight and tail length did a good job predicting the length of the cat's body. So we want to know how well weight and tail length predicts the body weight. Let's see. So here is an example. So body length and weight. So here is all the data in the graph. Now we do a least square fitting here. Since we have the extra term in the equation, we fit a plant instead of the line. So here you see, according to the equation, y equal to 0.3 plus 0.6x plus 0.75z. So there are some, like interesting factors in this equation. I would like to explain for you that y equal to 0.3. So the here is some of the factors are like intercept, some are like weight, and some are the tail length, right? So what is intercept? So intercept is basically where the line starts. Okay, so for example, the line is starting like maybe like 0.3 horizontal. So you can see that the line of the regression line is not exactly starting from 0. So it is starting from 0.3. So here you can notice that a key difference over here. So I can point here for you. So yeah, this is the point. So here is like 0.3, right? And here is 0.3. So this is called, like we call it as intercept, right? And this is like about the weight, okay, how the weight it will be affecting. So 0.6 with that one, and z the tail. So this is a new variable we have it. So we have like here two independent variables, which is about the tail length and the weight. So I hope like will be more clear to you. Okay, so let me disable this one. Okay, now let's see. Okay, now now we do a least square fit since we have the extra term in equations or extra variable, and we fit a plan instead of the line. So the equation predicts this body length. Okay, for example, given the weight and tail length of the cat, just like before, we can measure the residual, square them, and then add them up to the calculate r square. So let's suppose some of the z tail is like 0. Now if the tail length is useless and doesn't make SS fit smaller, then least square will ignore it by making that parameter, right? So now, for example, if some parameters are not useful like z, so we just like multiply with the 0 and remove it from the equation model. So in this case, plugging the tail length into the equation would have no effect on predicting the cat size. This means equation with more parameters will never make SS fit worse than equation with fewer parameters. So I hope this is understandable now. So cat size is equal to 0.3, which is the intercept from where the line is starting, cat weight. Then we can have favorite color, quiz grade, student name. So will never perform worse than the equation. Okay, so these are this is because least square will cause any term that makes SS fit worse to multiply by 0, and in the sense no longer exist over here. So due to the random chances in this equation, so there's acute or small probability that the small cat in the data set may be the best fit grade, or can have then multiple choices for the large cat. So the more parameters we add to the equations, the more opportunities we have the random events to reduce SS fit and result in better R square. So usually we need to go for better R square. So R square is very important for us. So the people report on the adjusted R square value that in essence scale R square by the number of parameters. For example, if we take 2 points, we always get a straight line with R square equal to 100%. Okay, so by this way, we need a path or a way to determine if R square value is statistically significant or important for us or not. So in some time, if R square is not helping us, so we need another test, just like a medical doctors, they have different tests for for diagnosing the disease. Similarly, we also have different tests for prediction. So first we went for R square, and now we are going for the p-value test. So let's see how the p-value is helping us in reduction in the variance. Okay, because variance is not good thing, is not needed thing. So variation in the cat size explained by the weight, okay, divided by the variation in cat size without taking the weight into the account, right? Okay. So R square is basically variance in the cat size, okay, and then we have variance after taking weight into the account, and then divided by the variance of the cat size. So this was discussion about regression model, and then we have some more advanced form of the linear regression. We have regression models, and we have linear regression when there is no curve, and if there is a curve, we call as a curvilinear regressions, or we can say non-linear as well. So here in this one, if you see whether where is a strong relationship, so if the variance is less, if the points are more closer to the line, so we see there's a strong relationship between the points. But when there is the points are far away from each other, so it means there is a weak relationship, and the prediction strength becomes lower. And here is no relationship sometime. So regression analysis, it is usually used to predict the value of the dependent variable, as I discussed in the previous point, that from the independent variable you find the dependent variable, like x was a dependent variable and x was independent variable and y was independent variable, and others are parameter like a and b, which is b multiplied with the x. So any value which is multiplied with the independent variable, that is considered to be a as a parameter. So these are like discussions. So we'll talk more on this linear regression in the next video. So thanks for now. Take care. Bye bye.